Welcome to big old chapter 6. We're going to be talking about exponential functions, something called logarithmic functions. We'll talk about what those are later, but we're going to start by talking about exponential functions and a little bit of applications now and a ton of really interesting applications at the end of the chapter. But I'm getting ahead of myself because I am getting excited. Okay, slow down. We're going to start by talking about exponential growth and exponential decay, something that we're all familiar with to some extent, I think. The spread of diseases a lot of times is exponential growth, okay, for example. So let's just start by kind of introducing an exponential equation and what it looks like. Graphing's not till 6.2, but this will introduce some topics. Example 1. Graph y equals 3 times 2 to the x. This is an exponential function because the exponent is where our variable is. Okay, and so in this graphing problem, I want to start by making a very quick note. Right? Note, you can't combine these. You can only combine exponentials when they have the same base. All right, so these are different bases. This is a base of 3, base of 2. So this is not 6 to the x. That's very different. So be aware of that. Can't just combine because one of them has an x. They're essentially not like terms. You can think of it kind of that way. Okay, so we want to graph this. So I'm going to go over here, get my graph paper. And we'll be using Desmos to graph most things. But hold on, I'm going to cheat by looking ahead. But this one, I really want to graph with an actual table. So we're going to make a table of a bunch of x values and a bunch of y values. And really graph this the old-fashioned way. So let's just plug in some x values. A lot of times I like to start with 0. So if you plug in x equals 0, what do we get? We get y equals 3 times 2 to the 0th power. Remember your properties of exponents. Any number that's not 0 to the 0th power is 1. When x is equal to 0, y is equal to 3. And again, I'm going to cheat a little bit. This is going to get really, really big. Okay, let's count by 2's over here. Say this is 2, 4, 6, 8, 10, 12, 14, like this. But we'll count by 1's in the x's, and that's okay. Your scale for your x's doesn't have to be the same as the scale from your y's. So when x is 0, y is equal to 3. That's this point right here. Well, let's keep going. When x is equal to 1, what do we get? Y is 3 times 2 to the 1st power. Is 3 times 2 is 6. When x is equal to 1, y is equal to 6, like so. I'd highly recommend you pause the video right now and do the same thing for 2, for 3, for 4, and for some negative numbers, -1, -2, and -3. So pause the video, figure out the y values here, and then we'll go through it together. All right, you do the calculations for 2, you should get 12. For 3, it's going to be 24. For 4, you should get 48. For -1, you should get 1.5, and then 0.75, and then 0.375, I think. And we can plot these points. So 2, 12, that's right here. 3, 24, that's somewhere way up there. I don't know. It's too big. It doesn't fit anymore. -1, 1.5. Remember, 1.5 is going to be 3/4 of the way to 2. And then we cut that in half. And then we cut that in half. Notice what's happening with all the y values, right? As we move to the left, we're cutting the x value in half, or the y value in half, right? We're at 1.5, move 1 to the left, cut that in half to 3/4. As we're going to the right, we keep doubling. We're at 3, we move the right 1, now we're at 6. We're at 6, we move to the right 1, now we're at 12. This is not a coincidence. We keep doubling. But either way, at the end of the day, you connect these points, you'll do it better than that. If you connect these points, we keep on to the left, keep on cutting our thing in half. We get closer and closer to 0, closer and closer to a y value of 0, but we never quite hit it because we keep cutting it in half. Oh, we're going to have an asymptote. We're back with asymptotes, okay? So this is what we have got right here. So a lot of things that we can say. And so we're going to say them. Hopefully, by the way, this looks like the actual graph. You can check your answers using Desmos, right? Y equals 3 times 2 to the x. What happens? Well, we start at 3. Great. And every time we move right 1, we should keep doubling. Right 1, oh, up to 6. Right, another one, oh, up to 12. And so on. Okay? This should look like what we have. It hit the wrench icon on the right and make it even more similar. You know, let's do it, right? Let's go, x is from -5 to 5. Let's say y is like this. Should look pretty similar. Yeah, looks pretty similar. You could even do more to make it more similar, but don't need to spend too much time on that. So let's kind of summarize this information, okay? Let's summarize what we kind of have hinted at with these exponential functions. An exponential function is of the form y equals a times b to the x. And this exponential function has a couple properties. First off, a. So leave a big space here, or just don't write anything down yet. What is the a value? So a is the number before the exponential part. It's a number times b to the x. So in our example, a was 3. What did 3 correspond to? Corresponded to that y-intercept. If I change it to 4, what happens to the y-intercept? The y-intercept becomes 4. If I change it to 2, the y-intercept becomes 2. If I change it to -1, oh, the y-intercept becomes -1. If I change it to 0, yeah, don't do that. You multiply it by 0, the whole function's 0. Don't multiply it by 0. 1, y-intercept of 1, and so on. So a is always going to be the y-intercept. It has y-intercept a. Next up, what is b going to represent? This one's a little harder to see. But remember, we kind of mentioned it in the last one when we had 3 times 2 to the x. That means every time we moved 1 unit to the right, we doubled. So let's play with that. If I make it 3, do we keep tripling? 0, 1, 1, 3. Okay, that's tripling. Do we have 2, 9? 2, 9. It's like right there somewhere. Yeah. So if b is equal to 3, we keep tripling. What if this is a fraction, like 1/2? If it's 1/2, will we keep halving? Oh, interesting. We start at 1, so we move 1 unit to the right. We're half of what we used to be. Another unit to the right. We're half of what we used to be, 1/4, and vice versa. Okay, so yeah, this would be decay. Excellent. So B is that growth rate. Sometimes it's also called the decay rate. Look, I even left enough room for myself. And so again, as a note, right, it's growth. Oh, hold on, let's color coordinate it. Decay, because red is usually more used for decay, I don't know. Decay is if B is between 0 and 1. Growth is if B is bigger than 1. Now notice that this does not include all the values of B. It doesn't include B equals 1, right? We're either bigger 1 or less than 1. Why can't B equal 1? Well, let's look at a growth rate of 1. Oh. It's because 1 squared, 1 cubed, 1 to the 4th, it doesn't change anything. So this is another boring situation. B equals 1 is not interesting. We also said B can't be negative. What happens if B is negative 2? Whoa! This is bananas. We're not going to worry about this real quick, but this is why we're saying that B can't be negative. Has to do with square roots of negatives not being real and stuff like that. But yeah, this is something funny to look at that we're not going to talk about. And that's why we're requiring that B is positive. Okay. Last thing, asymptote. There was a horizontal asymptote right here on the y-axis. What's the equation of that? Horizontal line. So it's y equals. All right, so it's horizontal. Always of the form y equals blank. So that's the basics of exponential functions. Let's do some problems. Example 2. Identify the starting value otherwise known as the y-intercept, and the growth or decay rate for the following. Part A. Y equals 1/2 to the x. So keep in mind, right? This is what we were just talking about. Y equals a times b to the x. A is the y-intercept, the starting value, and b is the growth rate or the decay rate. So right off the bat, the starting value is this a. No, I don't see anything there. If you don't see anything, remember that you can think about that as 1 times. Okay, so the starting value is the y-intercept. Is 1. All right, do we have growth or decay? Well, is this number bigger than 1? Or between 0 and 1? Between 0 and 1. This is going to be decay. And our decay factor is 1/2. Every time we increase x by 1, we're going to get cut in half. All right, and that's what we have here. We can do this with another one. 3 times 2 to the negative x. Ooh, this one's not in the same form. What's the difference? The difference is that little negative right there. So what we're going to do is we're going to make it into the same form. Remember properties of exponents. If you need to review properties of exponents, feel free to reach out for some materials, or you can just Google property of exponents. Properties of exponents. There's a lot of good ones in there that we're going to be using more and more as this chapter goes on. And I'll make little review comments like this, but you might want more. If I have any number to a negative exponent, That's the same as 1 divided by that number to the positive exponent. Negative exponents just mean reciprocal. Okay? And you can also think about that as 1 over a to the n as well. That's what we're going to do right here. This is the same thing as 3 times 1/2 to the x. Don't believe me? Graph it on Desmos. So again, the starting value is that a value. And again, we have a decay rate or decay factor, whatever you want to call it, of 1/2. Let's do part C real quick. Y equals 0.5 times 1.5 to the x. Starting value is 1/2. And now we have a growth rate or growth factor of 3/2 or 1.5. It's bigger than 1. That's how we can identify whether something's growing or shrinking. If you forget, go over here, type it in. What does 3 times 2 to the negative x look like? It looks like it's decaying. Move left to right. It is getting smaller. Okay. All right, one last problem. Just to reinforce how to evaluate things. This should be pretty straightforward. Evaluate, and then round to 4 decimals if you need. F of x equals 2 times 5 to the x, and I want you to find f of -3. All you do is plug in -3, like we've been doing before. So 2 times 5 to the -3. You can do this by hand. Negative exponents means reciprocal. 5 cubed is 125. We'll get 2 over 125 is our exact answer. Or you can type it into a calculator, right? Desmos helps us as well. 2 times 5 raised to the -3 is 0.016. Make sure when you're doing exponentials, let me just verify that this is true. All right. It's a good idea to put parentheses in the exponent, but it turns out that Desmos doesn't require you to. Your own calculator may be different if you're not using Desmos. Parentheses are a good idea for these exponents. And remember shift 6 or that caret, that gets you into the exponent. All right, and we'll do one more, kind of a sneaky one. F of x is equal to e to the x. Find f of 3. We haven't mentioned e yet, so I'm not going to go into it now. But you can still use your calculator the same exact way. Your calculator should have an e button on it. E is a number. We'll talk about it more in a later video. And Desmos also, I believe, functions with e. E raised to the 3rd power is about 20.0855. All right. And we'll talk more about e later. And last problem, we'll just do it real quick. Why not? F of x equals 2.7 times 4 to the -x plus 1 plus 1.5. Evaluate f of -2. So this one's a little messier. Be very careful typing things into your calculator. You can also do this one by hand. It'll take a little longer. But you'll write it as 2.7 times 4, and then it's a good idea to use parentheses. We have -x, and x is -2. This becomes a positive 2 plus 1, or just 3. And you can type that into your calculator. So you should get 2.7 times 4. Whoa. 2.7 times 4 cubed plus 1.5, 174.3. All right, so get some practice using your calculators. Can also use Desmos. Enjoy.